This is Physics 2211 Lab 4 going over oscillations. Now in the lab we'll be examining the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and we'll compare both an experimental and a computer model. Now we need to know some fundamental principles before we begin. Firstly, the force of gravity and the spring force, and then we also need to know that to get the net force we need to add these two together. We also need to know the potential energy for gravity and the potential energy for springs, and then the kinetic energy, and we need to know that we need to add all these three together to get the total energy of the system. We also need to know the velocity update formula and the position update formula for the computational model, just updating all the values and variables within the calculation loop. This is the tracker video that just extracts the position over time for both the X and Y components, and the first split second is just used to calibrate the video, and as you can see, the mass on the spring is just doing more of an elliptical motion, and then the origin is set to this fixed attachment point at the top of the system. Now first we need to calculate K using information from the video, and we can use the period of oscillation formula, and because we know that the period of oscillation is equal to 1.524 seconds, and we know our mass is equal to 0.402 kilograms, we can essentially plug these values in and isolate K to get our stiffness value of 6.83 newtons per meter. We then need to calculate the resting length from the video, and we can do this by taking our force of gravity and equating that to the spring force. So we get mg equals ks, and then we can isolate for the resting length of the spring because we know our stretched length as well as mass, gravity, and then we just found our stiffness constant. So we can plug all that in and isolate the resting length to get the resting length to be 0.123 meters. We then, for the actual computer model, we need to set some initial conditions, such as the ball's mass and then initial position, and the velocity is set to 0 because we hold the thing initially and then let go of it, so the initial velocity should be 0 seconds in the video, or 0 meters per second. And then also we need our gravitational force near the surface of the Earth, the spring constant that we found, the relaxed length of the spring that we found, and then we need to set some initial energies, such as kinetic energy and then potential energies. This is the calculation loop that updates everything. So we take our initial energies and then we calculate the different forces and add them to get net force, which is then used to update the velocity and position accordingly. And then we need to actually update the spring in the computer model and then calculate the energy changes by calculating the new energies based off of the velocity and position, and then subtracting the initial energies from this to get the change in energy. And this is just a little snippet of it visualized, where the blue ball is the actual computer model and the red ball is the actual experimental data. And as you can see, the two data sets are very similar. With the red ball, it's a little different, but that's likely just because of inconsistencies, clicking a consistent center of mass, as well as setting some initial conditions correctly, such as position. This is the change in energy versus time graph, with blue being the change in kinetic energy, red being the change in gravitational potential energy, green being the change in the spring potential energy, and then orange being the total change in energy. This is position versus time data, where red is the experimental data and blue is the model data, and the left graph is the x position, y graph is on the right. As you can see, these stay pretty close to the actual model data, the experimental data, except we do have some differences, and this is once again likely to just setting initial conditions and then clicking center of masses consistently in the tracker software. Now for the model system, is the energy principle satisfied? And in short, yes it is, and this is just because we set the system to be everything, so there should be no change in the total energy, which would be represented visually by a consistent horizontal line by delta E. It should be at 0 joules for the entirety of the graph, which we can see that with some deviation, very slightly, but for the most part, it does stay at 0 joules the entire time. Now, we can also go on to estimate the oscillation periods for the x position data and the y position data. So in order to be accurate, rather than just using one period, we'll use 3. So for the x data, we get 5.381 seconds for 3 periods, and dividing that number by 3, we get 1.77 seconds for for one period. And then the y data, we do the same, and we get 1.67 seconds for the period of oscillation for the y data. And this makes sense because the x and y components are obviously impacted by different things more than the other ones are. And the x component here is more impacted by the gravity and length, whereas the y component is actually impacted more by the stiffness and the mass.